Hi, let's talk about Archimedes Principle, one of the oldest scientific principles that you will learn about in a modern physics book. And the legend of Archimedes Principle is that Archimedes was brought in to solve a dispute between a ruler of a town in Greece and a jeweler who the ruler had convinced to make a crown for a statue honoring one of the gods. And the ruler was absolutely convinced that the goldsmith mixed in a little bit of cheaper silver from the pure gold that he was given and pocketed the excess gold and returned a crown that had the same mass as a crown of pure gold, but with that cut silver actually wasn't pure gold. Now, the legend of Archimedes is that he was in the baths, he dipped his toe in the bath, saw some water spill out, and then started running naked through the streets of town shouting Eureka, which is the Greek word meaning I figured it out. Now, ancient historians have, starting in about 500 years after the time of Archimedes, reported that Archimedes' idea was to take a look at the change in volume. And by measuring the volume displaced by the crown, the volume displaced by pure gold, you could calculate densities and from that figure it out, which wouldn't work. Because even in today's times, it is tough to measure volume to a high enough precision to actually make that happen. And a lot of Greek work survives from antiquity. It just got lost to Roman scholars, and even at the time of that history that was written, scientists recognized that that story was BS because they couldn't measure density precise enough in order for that to work. We'll talk about how Archimedes actually did it when we finish talking about his principle in action. And what Archimedes really said is, anytime an object is immersed in fluid, you take any object and dip it in fluid, it feels a net upward force called the buoyant force, and the buoyant force is equal to the weight of the fluid that's displaced by the object dipped in a fluid. So to show that, let's take an object that's fully submerged. And if you took a look at my discussion of where the increase in pressure at depth comes from, this should look almost exactly the same, because it is. Only I'm saying here that my box is some physical object that is being held fully immersed in a fluid. So there's a pressure on the top, there's a pressure on the bottom. The pressure on the bottom is greater than the pressure on the top because of the depth of fluid. And my change in pressure, as long as that object is surrounded by fluid, is going to be equal to the density of my fluid times the strength of gravity times the height of my object. And we're just going to work with a nice, simple shape where the height is uniform all the way around. If you were to take on even a more complicated shape, you would still end up with the exact same result. So, our net force then would just be our difference in pressure acting on our object times the cross-sectional area of our object. Well, our pressure change is the density of our fluid times gravity times the height of our object times the cross-section of our object. Height times cross-section is the volume of a uniform object. So the volume of the uniform object is the volume of fluid that got pushed out of the way, because this is totally inside that fluid. So that means then my net force is the density of fluid times the volume of fluid displaced times gravity, which is exactly the weight of the fluid displaced. It also explains the will it float game from late night television. It's fun to throw things in water and see will they float or won't they? Well, we could check it out just based off density. If the density of our object is less than the density of our fluid, the net force is going to be upward. So yeah, the object floats to the surface. If the density of the object is exactly the same as the density of the fluid, it floats by not sinking. It'll just stay in place. Fish submarines, things that try to spend all of their time underwater, they're able to adjust their density to match the density of water so that they're what we call neutrally buoyant, and they don't have to expend any energy either fighting sinking or fighting floating, which if you want to stay underwater is a pretty efficient way of doing that. And if the object is denser than the fluid, then the object is going to sink. So, fun fact, the density of mercury is greater than the density of lead. Solid lead floats in mercury. Now, let's get back to what Archimedes actually did. So, Archimedes' idea was a very high precision way that we use essentially today to determine the density of objects to high precision. So what he did was build a balance, and he built it in a tank that could be filled with the fluid. And then he got a sample of the exact same gold that was given to the jeweler, and he placed the crown on one pan of his balance and balanced it out with gold from that supply. Now, once that was balanced, he filled this with fluid. Well, when this was built, if it was empty, it balanced empty and balanced while submerged in fluid. So, if the gold of the crown was exactly the same as the density of the exact gold, it would displace exactly the same volume, so the net force on each object would be the same and the scale would stay balanced. Now, if the crown was cut with less dense silver, the crown would experience a net upward force and the scales would be out of balance, which is, unfortunately for the jeweler, exactly what happened with Archimedes' Principle. So, a cool thing that you can do, and I mentioned we use this all the time, particularly in the ceramics industry. With ceramics, you're trying to fuse together a whole bunch of little tiny grains and get them to as close to the density of one crystal of that object as you can actually get. And the more air pockets you have, the lower the density is, the more likely the ceramic is to be brittle or to not have any of the properties that it needs to have. Well, if you take this equation for the net force by being the volume of a fluid displaced, that would be equal to the mass of an object when it's being measured in air times gravity minus the apparent mass of an object if you were to, similar to this Archimedes balance, just suspend an object inside a fluid and measure its mass through some sort of balance that you have calibrated so that it would work in air and inside that fluid with only the object experiencing that buoyant force. Well, if we take this and rearrange it, the density of our fluid times our volume would be the actual mass minus the apparent mass. Well, we have the volume of our object, we have the mass of our object, we can pull the density out of that. And with a little bit of algebra, you can show that the density of the object that you're dealing with is going to be the density of the fluid divided by 1 minus the ratio of the apparent mass of the object, the mass that you measure when it's suspended in a fluid, divided by the mass that you measure when it's in air. Thanks for watching.